Imagine this. You just spent, I don't know, hundreds of thousands of dollars on a state-of-the-art CNC Machining Center.
Right, which is a massive financial investment for any factory.
Oh, absolutely. And just for anyone who hasn't been on a factory floor recently, CNC stands for Computer Numerical Control.
Right.
Basically, you are buying a massive, highly advanced, precision-engineered robot, and it carves solid blocks of metal into these really complex parts.
Yeah, parts for, airplanes, medical devices, cars, that sort of thing.
Exactly.
Yeah.
So you bring this marvel of modern manufacturing onto your factory floor, right?
Mm-hmm.
You meticulously set it up and you get to work.
As you do.
But then, within just a few weeks, you look closer, and the heavy cast iron table of the machine, along with those incredibly precise alloy steel tool holders, they are completely covered in severe destructive rust.
Oh, man, that is a manufacturer's absolute worst nightmare.
Right.
I mean, you're looking at a massive financial investment literally eating itself alive in record time. And obviously, the precision of the parts you are making is completely compromised at that point.
And the craziest part about all of this, the culprit isn't the machine's quality.
No, it's
Not a
good.
factory defect. It is literally the fluid you poured into it.
Yeah, it's wild.
So welcome to our deep dive. Today, we're looking at a really fascinating stack of sources. Specifically, it's a highly technical troubleshooting guide focused entirely on CNC Machining Center coolant selection and maintenance.
Which sounds a bit dry, but I promise it's not.
Not at all. Our mission today is to uncover the hidden chemical warfare happening right now inside modern manufacturing equipment. We're going to figure out how a seemingly simple choice of liquid completely dictates the survival or the rapid destruction of these incredible machines.
Yeah, it sounds a bit dramatic, but honestly, understanding this hidden fluid dynamic is the ultimate shortcut to saving massive amounts of time and money in manufacturing.
Because ignorance here is expensive.
Right. Incredibly expensive. I mean, if you're operating this equipment, or even if you're just, fascinated by industrial engineering, knowing how the chemistry, physics, and biology of this liquid interact is absolutely non-negotiable.
Okay, let's unpack this. Because before we can even talk about how the machine breaks down or rusts, we really need to understand the terrifyingly extreme environment happening right at the cutting tip of the machine.
Right, the actual point of contact.
Yeah, because naturally you hear the word coolant, and you think of like a car radiator.
Oh, okay.
Or you just think, oh, just splash some water on the metal, keep it from getting too warm.
Right, just hose it down.
Exactly.
Yeah.
But water alone doesn't even come close to surviving what is actually happening inside the cutting chamber.
No, not even close. I mean, if we look at modern high-speed 5-axis machines, the environment at the cutting tip is just extreme.
How extreme are we talking?
Well, you have to remember, a machine tool doesn't slice through solid steel or titanium the way, like, a knife slices through an apple. It's a violent, high-friction shearing process. The tool is literally tearing the metal apart at a microscopic level.
Carrying it well.
Yeah, and because of that immense friction, the instantaneous temperature right at that tiny contact point between the tool and the workpiece, it easily exceeds 800 degrees Celsius.
800 degrees Celsius. That is basically the temperature of flowing lava.
It is staggering heat, and, it happens in a fraction of a second.
So if your fluid can't handle that.
If your fluid fails to absorb that massive heat instantly, you experience severe thermal expansion. The metal part you're trying to cut will physically expand and warp from the heat.
Which completely destroys your dimensional accuracy.
Exactly. And even worse, the expensive carbide cutting tool itself will simply overheat, soften, melt, and shatter.
It makes me think of an analogy, like trying to cool down a CNC cutting tool at 800 degrees Celsius is like trying to put out a fire on a rocket engine with a fire hose.
That's a good way to put it.
But while you're blasting that fire hose, you simultaneously need that exact same water to act like the world's most slippery oil to stop the metal from fusing together.
That is a brilliant way to picture it, actually, because heat extraction is really only half the battle here.
Right.
The fluid also has to act as a heavy-duty lubricant under immense physical pressure. As the machine carves into the workpiece, the coolant has to maintain a strong microscopic boundary layer.
Like a tiny liquid film.
Yeah, a liquid film between the tool and the raw metal. Because if that film breaks down, the immense pressure and heat will cause the metal cutting tool to physically weld itself to the workpiece.
Just instantly fused together.
Literally friction welded.
And we aren't just talking about, like, a gentle misting system here either. To penetrate that heat and friction, this fluid is being blasted at the cutting zone like a pressure washer.
Right. far stronger than a standard pressure washer, actually. Modern machines use high-pressure delivery systems that pump this fluid directly through the center of the cutting tools at up to 150 bar.
Wait, 150 bar? For context, that's over 2,100 pounds per square inch.
It is a massive amount of force.
Yeah.
And it needs that extreme mechanical force for a very specific reason, which is to evacuate the metal chips instantly.
Oh, to get the shaved metal out of the way.
Exactly. If the fluid doesn't blast those tiny razor-sharp pieces of cut metal out of the way, the spinning tool will end up recutting its own broken chips.
Which I assume is bad.
It destroys the cutting edge immediately.
Wow. So just to summarize the sheer physics of this, we need a fluid that can handle over 2,000 psi of pressure, instantly absorb 800-degree heat without just evaporating into nothing, violently flush away flying metal shrapnel, and maintain a microscopic lubricating barrier strong enough to stop two pieces of metal from friction welding together.
You've got it. The core requirements for this specialized fluid are incredibly strict. It demands absolute thermal stability so the chemical compounds don't just break apart under that 800-degree flash point.
Right.
It needs rapid heat conduction to pull that temperature away faster than the metal can absorb it. And it requires extreme pressure lubricity.
So pouring a standard liquid, or even just picking the wrong type of industrial coolant.
It guarantees a catastrophic failure under those conditions.
Yeah.
Absolutely guarantees it.
Which leads us perfectly to the next major section in our sources, because we've established that the fluid has to perform absolute miracles at the cutting tip.
Yeah, miracles is a good word for it.
And that means you can't just pick up a random bucket of fluid off a hardware store shelf and pour it into a $500,000 machine. The chemistry of the fluid has to be perfectly matched to the specific metal you are cutting.
This is where the physical engineering really turns into a complex chemistry problem. You have to match the fluid's formulation to the metallurgical properties of the workpiece.
Okay, let's take aluminum alloys, for example, since that's super common.
Sure. The sources state that if you are cutting aluminum, you absolutely need a synthetic or semi-synthetic fluid.
Why is that?
Because those formulas provide excellent cooling properties, and they leave a clean, bright surface on the finished part.
But let's say a shop makes a mistake, and they use a normal steel coolant on an aluminum part. What actually happens mechanically?
It really comes down to alkalinity. Normal steel coolants are highly alkaline.
To prevent the steel from rusting, I assume.
Precisely. But aluminum has a natural, very thin oxide layer that protects it. So the high alkalinity of a steel coolant chemically attacks and strips away that protective oxide layer on the aluminum.
Oh, wow.
Yeah, and once that layer is gone, the raw aluminum oxidizes wildly, staining the parts and actually turning them black.
Turning them black. So you end up ruining the entire production run.
The whole batch is ruined, yeah.
So aluminum strictly needs synthetic fluids to protect its chemistry. What about when a shop cuts incredibly tough materials like heavy steel or titanium aerospace parts?
For those heavy, tough metals, you need to switch to soluble oils. Synthetics just won't cut it.
Why not?
Because titanium and heavy steel generate much higher cutting forces, which means they require far superior extreme pressure lubrication.
Wow.
Soluble oils have a much higher concentration of actual mineral oil, which provides that heavy-duty lubricating film required to, wedge between the tool and the titanium without breaking down.
Hold on. I'm putting myself in the shoes of a busy shop floor manager here.
Yeah.
Realistically, factories cut different metals all the time.
Oh, constantly.
Right. So I might be running a batch of aluminum parts on a Tuesday morning and then switching over to heavy steel parts on a Tuesday afternoon.
Yeah, very common scenario.
So am I really going to drain a 100-gallon coolant tank, scrub it down, and refill it entirely every single time I change metals? Can't I just be a little lazy, leave the synthetic fluid in there, and just top it off with some soluble oil? I mean, lubricant is lubricant, right?
Doing that will shut down your entire factory.
Seriously?
The sources are definitive on this: never mix different coolants. It is a massive chemical violation.
What makes it so bad?
Well, these fluids contain specific chemical emulsifiers. They're compounds designed to keep the oil and water perfectly mixed together. When you mix a synthetic coolant with a soluble oil, those different emulsifiers actually attack each other, they break down, and the active chemicals literally drop out of the liquid suspension.
Oh, gross. And what does that look like inside the machine?
It forms a heavy, sticky, incredibly dense sludge. It has the consistency of, thick mayonnaise mixed with glue.
Ugh, Mayonnaise and glue. That sounds like a nightmare to clean.
It is. This sludge coats the inside of the tank, it completely clogs the intake filters, and it jams those delicate high-pressure nozzles we talked about earlier.
So your 150-bar delivery system is just rendered completely useless.
Completely useless. You're dead in the water.
Okay, message received, no chemical mixing. But the sources point out that the coolant concentrate itself is really only part of the equation. You have to mix that concentrate with water.
Yes, a lot of water.
And apparently you can't just stick a hose in the tank and use tap water.
Absolutely not.
Yeah.
Think about what is in hard tap water. It is full of dissolved minerals, primarily calcium and magnesium. When you introduce those dissolved minerals into your highly engineered coolant concentrate, especially under 800-degree heat, a chemical reaction occurs.
What kind of reaction?
The calcium and magnesium ions bind with the coolant's emulsifiers.
Oh, so the water itself is attacking the fluid.
Precisely. It strips the emulsifiers out of the fluid, causing the oil and water to physically separate.
Wow.
Furthermore, those bound minerals drop out of the liquid and bake onto the hot surfaces of the machine, creating a hard, chalky scale buildup.
So to create a stable fluid mixture, the sources mandate that you must always start with purified water.
Specifically deionized or reverse osmosis water, yeah, where those minerals have been entirely removed.
Okay, and even after you've sourced purified water and carefully matched your chemical coolant to your metal without mixing anything, the daily maintenance is still ruthless.
It never stops.
The source text emphasizes that operators have to test the concentration of the fluid every single day using a specialized tool called a refractometer.
Yes, a refractometer is a little handheld optical device. You put a few drops of the coolant on a glass prism, hold it up to the light, and look through an eyepiece.
And what are you looking for exactly?
It measures how much the light bends or refracts as it passes through the liquid, because denser liquids bend light differently.
Okay.
So looking at the line on the refractometer scale tells you exactly how much chemical concentrate is currently mixed into your water.
And the sources state this concentration ratio must stay strictly between 5% and 12%.
Yes, that is the sweet spot.
What happens if an operator gets busy and lets the concentration drop below 5%?
What's fascinating here is the ultimate irony of water-based coolants. If the concentration drops below 5%, the fluid completely loses its rust protection.
Which is wild because you're adding it to protect the machine.
Right, but you have to remember what the coolant is actually protecting the machine from. It is protecting the machine from its own water content.
Because water naturally oxidizes iron, it causes rust.
Exactly. So the coolant relies on a specific ratio of strong chemical rust inhibitors to constantly fight against the very water it is suspended in.
Oh, that makes so much sense.
Yeah, if you let that concentration dip below 5%, the rust inhibitors are simply too diluted to function. The water takes over, and your massive financial investment starts rapidly rusting away.
Here's where it gets really interesting to me.
Right.
We've spent all this time focused on the violent, high-pressure chemical balancing act happening right at the cutting tip.
Right.
But let's follow that fluid as it violently splashes away from the workpiece. Where does it go?
Everywhere.
Right. The sources point out that no matter how good your machine design is, this fluid inevitably sneaks into the machine's incredibly expensive movement joints, specifically the rails.
That is the tragic flaw of the system. The machine uses a completely separate, dedicated system of thick oil to lubricate its sliding rails.
Okay.
But because this high-pressure coolant is exploding off the cutting tool in every direction, it constantly bombards the protective metal rail covers.
And I'm guessing it finds a way in.
Eventually, some of that water-based fluid always finds a way to sneak inside and infiltrate the rail system.
It feels exactly like an autoimmune disease for the machine. Think about it. This specialized fluid is poured in to protect the cutting tool and cool the system down.
Right.
But secretly, it's sneaking into the joints, chemically stripping away the grease and eating the machine from the inside out.
That is a highly accurate way to visualize it. I mean, let's look at the mechanical damage it causes to the two main types of rails the sources discuss.
Okay, let's start with box hard rails.
Right, so box hard rails are essentially two massive blocks of solid cast iron that fit tightly together, designed for heavy, rigid sliding.
Got it.
If your sneaky coolant has a low concentration, meaning weak rust inhibitors, it causes heavy rust to form directly on those flat iron sliding surfaces.
And the text notes that this rust acts exactly like sandpaper.
It does. Iron oxide is highly abrasive. As that massive cast iron bed slides back and forth, it grinds that rust into the metal, badly scratching and gouging the flat iron. But it gets worse. The improper coolant also washes away the protective slideway oil.
Okay, so you lose your lubrication.
Exactly. And when that oil barrier is gone, you are left with two different types of bare metal exposed to a conductive fluid, which triggers something called galvanic corrosion.
Okay, let's pause on galvanic corrosion because that's a dense concept.
It is.
For anyone who hasn't encountered that term, it's basically what happens when two different types of metal are sitting in the same electrically conductive fluid.
Right. They essentially turn into a tiny destructive battery.
Yeah. An electrical current flows between them, and one metal literally starts eating the electrical charge and the physical atoms of the other metal, corroding it away at an accelerated rate.
Exactly. It is chemical degradation at the atomic level.
Yeah.
Plus, if the coolant formula doesn't have a strong washing ability, tiny metal chips from the cutting process get left behind, wedged under that heavy sliding bed,
Causing even deeper physical gouges.
Exactly.
So that's the nightmare scenario for heavy cast iron box rails. But the sources argue that the newer style linear rails face an even faster, more catastrophic problem.
Much faster. Box rails rely on flat surfaces sliding against each other. Linear rails are completely different. They don't slide.
How do they work then?
They use tiny, highly precision machine rolling steel balls packed tightly inside a bearing block rolling along a track. They are built for incredible speed and accuracy.
That sounds delicate.
It is. Their major engineering weakness is that they have very poor internal protection against dirt and liquid contamination.
Which seems like a terrible design choice for a machine blasting fluid everywhere.
Yeah.
So what mechanically happens when that dirty coolant sneaks past the seals of a linear rail?
Well, the dirty coolant isn't just liquid. It is carrying microscopic metal dust, the tiniest shavings from the cutting process.
Okay.
It carries that abrasive metal dust right past the weak seals and deep into the linear rail blocks. Once inside, that metal dust mixes directly with the thick rail grease.
And suddenly your lubricant isn't a lubricant anymore.
No, the metal dust and the grease combine to create a thick, highly abrasive grinding paste.
Oh, that sounds awful.
It is. Instead of rolling smoothly, those tiny precision steel balls are now chewing themselves apart. That grinding paste will physically destroy the shape of those rolling steel balls in a matter of weeks, completely ruining the accuracy of the machine.
Let's put this in perspective for the listener. Because a factory manager didn't want to change, say, a $50 paper filter to catch that microscopic metal dust, the dirty fluid turns into grinding paste.
Yep.
Now, that manager has to pull their entire production line offline for 3 days to tear the machine apart and replace a $5,000 precision linear rail. That is a brutal return on investment for sheer laziness.
It is the ultimate hidden cost of poor fluid maintenance. The sources stress the absolute non-negotiable necessity of a high-quality coolant filtration system.
You have to catch that dust.
You must capture that metal dust before the fluid circulates back to the cutting zone, or your linear rails are doomed.
So what does this all mean? We have covered thermal destruction at 800 degrees. We've covered the chemistry of matching fluids to avoid the dreaded mayonnaise sludge.
Right.
We've covered the physical destruction of the rails via rust, sandpaper, and grinding paste.
It's a lot.
It is a lot. But honestly, the most surprising and somewhat disturbing part of these sources to me is what happens when the machine stops running and the coolant just sits still in the massive holding tank.
Oh, the tank. Yes.
Because the physical environment of that tank breeds a literal biological nightmare.
It is a massive, widely recognized issue in the machining industry. You can walk onto a factory floor, and occasionally you are hit with a smell that is overwhelmingly foul.
Like rotten eggs.
Exactly like rotten eggs. And it is not just an unpleasant odor. The gas being produced actually irritates the eyes and makes the workers feel physically sick.
How on earth does a high-tech, precision metal cutting machine suddenly turn into a toxic swamp?
It really comes down to the perfect storm of biology and the machine's environment. First, water-based coolants are highly susceptible to biological growth.
Naturally.
Now, add the heat factor. The cutting process warms the water up, and the tank usually sits between 25 and 43 degrees Celsius.
Which is pretty warm.
Yeah, and this is especially problematic during the summer months in unair-conditioned factories.
So you have a massive tank of warm, chemically rich water. It's basically a heated swimming pool for bacteria.
It is. But the catalyst for the real disaster is the oil.
The oil.
Remember that slideway oil and hydraulic oil we discussed? The oil is used to lubricate the machine's joints.
Yeah.
Inevitably, the machine naturally leaks a small amount of those oils down into the main coolant tank. In the industry, this leaked fluid is called tramp oil.
Because oil is lighter than water, I assume this tramp oil floats right to the surface of the tank.
Yes. It floats to the top and forms a thick, continuous, unbroken blanket over the entire surface of the water.
Think of that tramp oil blanket, like throwing a thick, heavy plastic tarp over a swimming pool in the dead of summer and just leaving it there.
That's exactly what it's like.
The water underneath is trapped, baking in the heat, completely choked off from the fresh air above.
That analogy is perfect because choking off the air is exactly what causes the biological crisis. That oil blanket completely blocks ambient oxygen from dissolving into the water below.
Okay, so no oxygen.
So now you have a tank of warm water with absolutely zero oxygen. This creates the absolute perfect breeding ground for anaerobic bacteria.
Anaerobic literally means they survive and thrive in environments where there is no oxygen.
Exactly. Protected by that oil tarp, they multiply exponentially.
And they aren't just swimming around. What are they actually eating down there in the dark?
They're actively consuming the chemical components of your expensive coolant.
You're kidding.
No, they eat the emulsifiers and the rust inhibitors, and as they consume your fluid's chemistry, their metabolic byproduct, their biological waste, is hydrogen sulfide gas.
And hydrogen sulfide gas is exactly what produces that distinct, horrible, rotten egg smell.
Precisely. And beyond just smelling terrible and making the operators nauseous, hydrogen sulfide gas dissolved in water creates a weak acid.
Oh, no.
Yeah, so the bacteria are not only eating your rust inhibitors, they are actively making the fluid more acidic, which accelerates the rusting of the machine even faster.
That is just awful. Your fluid is being chemically degraded, your shop smells toxic, and your machine is rusting from the inside out.
It's a complete system failure.
Okay, so how is a machinist supposed to fight an invisible biological enemy inside a dark metal tank?
Yeah.
You can't just pour bleach in there, right? That would ruin the fluid chemistry.
No bleach, definitely not. The solutions provided in the text rely on elegantly manipulating the biology.
Okay, how so?
First, you have to break that suffocating oil blanket. Factories install a simple mechanical device called an oil skimmer.
How does that work?
It usually involves a slow-moving belt or disc that dips into the fluid, giving the floating tramp oil something to stick to, and automatically wiping it away, removing the blanket from the surface.
Okay, step 1, pull the tarp off the pool.
Step 2, weaponize the air. Since these are strictly anaerobic bacteria, oxygen is highly toxic to them.
Right.
The sources recommend installing air stones or aeration pumps, literally adding aquarium bubblers directly into the coolant water.
I have to say, when I read the words aquarium bubblers in this highly technical engineering text, I genuinely laughed out loud.
It does seem a bit out of place.
You have this $1 million, high-speed, 5-axis, 150-bar pressure manufacturing marvel.
Yeah.
And to keep it running smoothly and stop it from stinking up the factory, you have to go to a pet store and buy the same little plastic bubbler you use for a goldfish.
I know, it sounds absurdly low-tech, but the biology really doesn't lie. By pumping oxygen directly into the water, you create a highly oxygenated environment that instantly kills off the anaerobic bacteria colonies. It is cheap and incredibly effective.
That is just brilliant engineering through simplicity.
And you reinforce that biological warfare with chemical control. The operator must meticulously maintain the fluid's pH level between 8 and 9.5.
Which makes it basic.
Right. Yes, this creates a highly alkaline environment. The science is simple. Bacteria simply cannot physically survive or reproduce in a fluid with a pH above 9.
So to recap the biological defense strategy, you skim the oil to remove their shelter, you pump in oxygen to poison their environment, and you spike the alkalinity to make the water itself uninhabitable for them.
Exactly. And finally, as a physical preventative measure, the sources mandate that you must constantly circulate the fluid daily and shovel out the piles of raw metal chips that settle at the bottom of the tank.
Oh, because they create hiding spots.
Yes, if you leave those piles of metal sludge sitting there, they create stagnant, dark microenvironments.
Perfect little caves where bacteria can hide from the oxygen and multiply all over again.
Exactly.
It's just incredible. Choosing a CNC coolant isn't just about casually buying a liquid from a catalog and pouring it in.
Not at all.
It is a rigorous, daily, highly scientific balancing act.
Yeah.
You are basically managing an entire microscopic ecosystem inside a metal box.
When you synthesize all the information from these sources, it fundamentally changes how you view industrial maintenance.
It really does.
You aren't just greasing some gears and pressing a green button. You are playing the role of a chemist. carefully matching the fluid formula to the specific metallurgy of the workpiece.
Right.
You are a physicist, meticulously monitoring the fluid density and water concentration to stop the machine from chemically rusting itself to pieces.
Yeah.
And you are a mechanical engineer, ensuring highly efficient filtration, so microscopic metal dust doesn't turn into a devastating grinding paste that destroys precision rails.
And on top of all of that, you are acting as a microbiologist.
Exactly.
You have to constantly fight off anaerobic bacterial infections by deploying oil skimmers, managing alkaline pH levels, and dropping literal aquarium bubblers into the tank to oxygenate the water.
It is a stunning convergence of chemistry, physics, and biology, all executing simultaneously just to allow a spinning piece of carbide to cut a piece of steel.
Which leaves me with this final thought for you to mull over as we wrap up this deep dive. We naturally think of these massive high-tech manufacturing machines as cold, hard pieces of unfeeling metal.
Right, they just seem like objects.
They are rigid, deterministic, and strictly mechanical. But look at what we've learned today from tracing the life of this fluid.
They really cannot survive on their own. They require a perfectly balanced, constantly circulating, heavily oxygenated, pH-controlled fluid system pumping through their veins just to survive the day.
Exactly. If this vital fluid fails, their internal joints literally grind away into dust.
Yeah.
If the fluid stagnates, they catch a literal bacterial infection that makes the whole factory sick. It really makes you step back and wonder. With a staggering level of complex, biologically balanced care required just to keep them functioning, are these million-dollar industrial machines actually starting to resemble living, breathing biological organisms more than just cold tools in a workshop?